Spider silk appears simple, yet it manipulates light through precise physical mechanisms. When sunlight strikes a web, specific wavelengths are diffracted by fibers comparable in size to their own length. This creates iridescent highlights that serve no decorative purpose, but result from fundamental wave interactions with protein structures. Now we move from observation to mechanism. Understanding these visual effects requires examining the physical constraints imposed by wave physics. We will analyze how specific structural features dictate light behavior without relying on mathematical derivations or abstract theory. Spider silk is often celebrated for its tensile strength, yet it functions equally as a sophisticated optical medium that interacts with electromagnetic radiation. When sunlight strikes the fiber, specific physical properties cause light waves to bend and scatter in predictable patterns. This interaction transforms the web into a dynamic display of iridescence, where color shifts depend on viewing angle rather than pigment. Consider how a prism separates white light into a spectrum. Similarly, silk fibers manipulate incoming photons through their cylindrical geometry and refractive index. The resulting visual effects demonstrate that natural fibers are engineered to manage energy transfer at the microscopic scale. To understand these effects fully, we must first define diffraction and interference within the context of fibrous structures. Pause 0.8 When light encounters an obstacle or opening comparable to its wavelength, it does not simply travel in a straight line, but bends around the edges. This bending phenomenon is known as diffraction, which fundamentally alters how waves propagate through space. To visualize this mechanism, consider water waves passing through a narrow gap, where they spread outward into circular patterns rather than continuing linearly. Similarly, when light interacts with a cylindrical fiber boundary like spider silk, the wavefronts curve around the structure, creating interference patterns. These overlapping wave interactions result in constructive and destructive regions that determine the observed optical effects on natural fibers. Understanding these wave behaviors requires examining how the specific diameter of spider silk fibers modulates these diffraction effects. Pause 0.8 When light encounters a spider silk fiber, the physical width of that strand acts as the primary filter for which colors become visible. This phenomenon relies on diffraction, where waves bend around obstacles and interfere with one another based on their spatial relationship to the wavefront. The diameter of the dragline silk determines exactly which wavelengths undergo constructive interference versus destructive cancellation in the observer's line of sight. Consider a simulated comparison. A thicker fiber with a diameter exceeding 500 nanometers will diffract longer red wavelengths more effectively, while a thinner strand around 200 nanometers preferentially scatters blue and violet light. This direct correlation between dimension and wavelength selection means that subtle variations in silk thickness create the iridescent patterns we observe on living spiders. Understanding this geometric constraint sets the stage for examining how surface irregularities further modify these optical effects. Pause 0.8 The surface of spider silk is not optically smooth like a mirror, but possesses microscopic roughness that fundamentally alters how light interacts with the fiber. When incident photons strike this textured interface, they encounter irregularities comparable to or larger than their wavelength, which forces scattering in multiple directions rather than a single reflected path. This mechanism distinguishes diffuse reflection from specular reflection, where smooth surfaces would preserve the angle of incidence and produce a coherent glare. Scanning electron microscopy reveals that these surface undulations act as countless microfacets, each redirecting light vectors away from the source direction to create a soft luster instead of sharp highlights. Consequently, the silk appears matte or pearlescent depending on viewing angle because the scattered photons reach the observer from varied trajectories rather than a single geometric reflection. Pause 0.8 When light encounters the boundary between spider silk and air, a fundamental optical phenomenon occurs due to refractive index mismatch. The protein core of the fiber possesses a higher density than the surrounding atmosphere, creating a distinct interface for electromagnetic waves. This difference in material properties forces a portion of the incoming photons to reflect immediately upon contact with the surface. Consider a beam of light striking a cylindrical silk strand. While some energy penetrates the protein matrix, another fraction bounces back into the air. The magnitude of this partial reflection depends directly on how sharply the refractive indices diverge between the two media. This boundary behavior sets the stage for understanding how internal structures further manipulate light within the fiber itself. Pause 0.8 The optical behavior of spider silk arises from its internal nanostructure rather than surface texture alone. Within the protein fiber, regions of tightly folded beta sheets form crystalline domains embedded in a disordered amorphous matrix. These alternating layers create a periodic variation in refractive index that governs how light propagates through the material. When photons encounter these interfaces, they undergo scattering events determined by the spacing and orientation of the protein chains. Consider a cross-sectional model where crystalline domains act as discrete lenses bending light paths toward specific angles. This internal architecture differs fundamentally from bulk glass because the scattering occurs at nanometer scales rather than macroscopic boundaries. The precise arrangement allows selective manipulation of wavelength-dependent diffraction patterns within the fiber core. Understanding this structural basis prepares us to examine how reflected light undergoes polarization changes upon interaction with these surfaces. Pause 0.8 When light strikes a spider silk fiber, the interaction fundamentally alters its polarization state through reflection and scattering mechanisms. Unpolarized sunlight contains electric field vectors oscillating in all directions perpendicular to propagation. Upon reflecting off the cylindrical surface of the silk, these vectors align preferentially parallel to the fiber axis due to geometric constraints. This selective alignment transforms incident unpolarized light into partially polarized reflected light with a distinct orientation. Consider how this differs from reflection off a flat glass surface, where polarization depends on the angle of incidence rather than structural geometry. The resulting polarization signature serves as an optical cue that predators or prey can detect through specialized visual systems sensitive to directional light oscillations. Pause 0.8 Spider silk functions as a dynamic optical system where environmental humidity directly modulates physical dimensions and refractive properties. When moisture molecules bind to the protein chains within the fiber, they induce a swelling effect that increases the overall diameter of the strand. This expansion alters the spacing between internal structural layers, which shifts the wavelengths of light that undergo constructive interference. For instance, a dry silk fiber might reflect blue-green hues due to its compact structure, but under high humidity that expands and reflects longer red-orange wavelengths instead. The refractive index also changes as water content modifies the optical density of the material, further tuning the color output without any chemical reaction. This reversible mechanism allows the spider to maintain visual signaling capabilities across varying environmental conditions through passive physical adaptation. Pause 0.8 The observed diffraction patterns in spider silk raise a fundamental question regarding their biological function within an evolutionary context. Current hypotheses propose three primary mechanisms: camouflage through background matching, intraspecific signaling via polarized light reflection, or passive structural integrity enhancement. Consider the contrast between a leaf-mimicking orb weaver and a flagelliform dragline. The former utilizes refractive index gradients to reduce visual detection against foliage. In this composite visualization, heat maps indicate visibility levels, where high-contrast silk fibers stand out sharply against low-contrast backgrounds. This suggests that optical properties are not merely byproducts of material constraints, but may represent selected traits for survival advantages in specific microhabitats. Pause 0.8 To quantify the optical properties of spider silk, researchers employ a combination of goniometric and spectroscopic techniques within controlled laboratory environments. The primary instrument is a goniometer, which precisely rotates both the light source and detector to map angular reflectance profiles across the fiber surface. By mounting individual silk strands under tension on a calibrated stage, scientists can isolate how specific structural parameters influence light scattering without environmental interference. For instance, when measuring a dragline sample from an orb weaver spider, the goniometer records distinct peaks in specular reflection that correlate directly with cuticular layering and refractive index gradients. Complementary spectroscopic analysis then decomposes this reflected light into spectral components to identify wavelength-dependent absorption features inherent to the protein composition. This dual approach allows for a rigorous separation of geometric diffraction effects from material-specific optical responses, establishing a baseline for comparative analysis. Pause 0.8 To understand the unique optical properties of spider silk, we must contrast them directly against manufactured polymer filaments like nylon or polyester. While both materials are fibrous and capable of diffracting light, their internal molecular structures dictate fundamentally different diffraction patterns. Spider silk possesses a semi-crystalline arrangement where protein chains align in precise, periodic domains that create sharp spectral peaks through constructive interference. In contrast, synthetic fibers typically exhibit amorphous regions with irregular chain packing, resulting in broader and less defined scattering profiles. Consider the visual evidence on screen. The left graph displays the narrow reflectance bands of spider silk, whereas the right shows the diffuse spread characteristic of fishing line. This distinction arises because natural selection has optimized silk for structural integrity and light interaction over millions of years, unlike industrial polymers designed primarily for tensile strength. These comparative data points highlight how biological engineering achieves optical precision that synthetic manufacturing struggles to replicate without complex processing. However, even with these clear distinctions, our current theoretical frameworks face challenges when attempting to model such complex natural systems accurately. Pause 0.8's current optical models often treat spider silk as a uniform dielectric cylinder with constant refractive index. This simplification ignores the dynamic protein folding states that shift during hydration cycles in natural environments. When we compare theoretical diffraction curves against empirical measurements, significant deviations emerge at specific angular intervals. For instance, hydrated silk fibers exhibit scattering patterns that standard equations cannot predict without introducing arbitrary correction factors. These discrepancies highlight where simplified physics fails to capture the full complexity of biological material behavior. Understanding these limitations sets the stage for examining how evolutionary processes have optimized silk structure beyond simple geometric constraints. Pause 0.8 The optical properties we observe in spider silk are not the result of deliberate engineering, but rather the outcome of billions of years of evolutionary refinement. Natural selection has tuned these fibers to maximize light diffraction, enhancing camouflage and structural integrity without any conscious design process. Consider how a single protein chain folds into complex structures that manipulate light waves through precise molecular spacing, much like a finely crafted optical lens. This biological optimization demonstrates that physical principles can emerge from survival pressures alone, creating systems as efficient as those designed by human hands. This synthesis sets the stage for examining how these evolved optical mechanisms might inspire new materials science approaches. Pause 0.8 We examined how spider silk functions as an active optical medium rather than a passive structure. The interplay between fiber geometry, protein composition, and environmental factors creates complex light interactions that are measurable and predictable.